So, in a particular fission reaction, a uranium-235 nucleus absorbs a neutron and undergoes fission to a barium-141 nucleus and a krypton-92 nucleus. The reaction is as follows, okay? They give us the binding energies per nucleon, which are these ones here. Show that the energy released when one uranium nucleus undergoes fission in this way is about 200 MeV, okay? So again, let's remind ourselves that the mass energy or binding energy per nucleon is is less for the parent nuclei compared to the daughter nuclei, and hence energy will be released in the process. So first of all, we need to work out the binding energies of barium and krypton, add them together. So that's 141 times 8.4 if we want these in MeVs, because the final answer, they say they want something close in MeVs. So you want 141 times 8.4 plus 92 times 8.6, and that'll give us our total energy released. Remember, neutrons have no binding energy per nucleon, so we just ignore them. Then again, 7.6 times 235 for the uranium. So on one side, I'm going to have 7.6 times 235 for my uranium, and then obviously I want barium 141, and I want 92 Kr. So this is going to be 8.4 times 141, and this is going to be 8.6 times 92. Okay, so obviously plug those numbers into your calculator, and you should end up with 170.86 MeV for that one, and 1084 MeV, and then 791. So obviously we need to work out the difference. So I'm actually going to take these two, 1184 plus 791 minus my original 1786, and that should give me 189 MeV. Now we can say 189 MeV is approximately 200 MeV, which is what they want us to get. Okay, part B, it says calculate how much energy is released when 1,000 kilograms of uranium undergoes fission. Assume that every fission generates the same amount of energy as the reaction stated above. Okay, so first of all, we can work out the number of uranium atoms in that 1,000 kilograms, can't we? Because we've just worked out the energy released when one nucleus undergoes. However, we want to find out how many nuclei are present in 1,000 kilograms. Okay, so what do I need to do in order to work that out is, if you look at your data sheet, first page, they should obviously give you masses of different particles, and one of the particles they give you is the mass of a proton or a neutron, okay, or a nucleon. So that's the mass we're going to use, and we're going to divide 1 kilogram by 235 times the mass of either the neutron or the proton, and to 2 sig figs, you know, they're pretty similar. So again, we've got 1 kg of uranium-235. So I'm going to do 1 kilogram divided by my 235. So there are 235 nucleons in the uranium, and then I need to times the mass, as we've seen in the data sheet, 1.6 times 10 to the minus 27 kilograms, and that should then give me 2.55 times 10 to the 24 nucleons. Okay, so now we've got the number of nucleons, and if each nucleon gives off in one nuclear fission reaction 189 MeV, as we've worked out in the previous question, well, all we need to do now is just to multiply the 189 MeV by this number of nucleons in the 1 kilogram. So if it's just electron volts, then all we need to do is 2 times 2.55 times 10 to the 24 number of nuclei times the energy released per nuclei. Okay, and if we want it in joules, times 10 to the 6 times 1.6 times 10 to the minus 19 times 2.55 times 10 to the 24. Okay, and that will give you 7.7 times 10 13 joules. Hopefully that made sense. I'm going to move on to question 6 now. So this question is about particles, and there are antiparticles. State the mass and charge of an antiproton. Okay, so the mass should be exactly the same, and as we know, or we should remember that antiparticles are particles that have the exact same properties, mass, everything but the charge. Okay, so and again, you can find the mass in kilograms in your data sheet, and we've just used it, haven't we? It's 1.67 times 10 to the minus 27 kilograms. Its charge, however, so charge will be the negative of its standard positive charge, but bear in mind the proton's charge is with respect to the charge of the electron. So if the electron is minus 1.6 times 10 to the minus 19, that's going to be the charge of the antiproton too. Okay, because the charge of a proton would be positive, this number. Okay, so that's 6A. Okay, 6B, state where an antiproton might be found. Well, they can be found in particle accelerators, so let's write that down. So in particle accelerators, for example, the Large Hadron Collider, but also they can be found in cosmic rays. And then C, when a proton and an antiproton meet, gamma photons are produced. Describe these photons as fully as you can for a slow-moving proton and proton-antiproton collision. No calculation is required. So this comes to what we call pair production. This is annihilation, not pair production. So this is obviously a standard proton colliding with its antiparticle equivalent. What happens when they collide? Well, actually we get two beams of gamma photons, okay, of equal amount of energy, but the total energy will obviously equal the rest mass energies of the two protons plus their kinetic energy with which they're moving at. Okay, so rest mass energy is obviously your E equals mc squared. So that's your rest mass energy. And then you obviously have your kinetic energy equation. Okay, so both these energies have to add up. So if I was to write this down, so I'm going to say 2 times mc squared, where m is the mass, so mass of proton slash antiproton, because obviously they'll have the same mass. Okay, plus 2 lots of their kinetic energy, because we're told that they're moving. Now the total sum of these two energies has to equal the energy that gets released in the collision, in this annihilation collision. And you should know from the photoelectric effect, okay, this equation here, where E is equal to Planck's constant times the frequency. Okay, so we can then, and for each of the gamma photons, they're obviously going to have energy of a set frequency. So that is going to equal to H2HF. Okay, where HF is equal to the energy of one gamma photon. Okay. Describe these photons as fully as you can. Okay, so basically we have to say 2 photons will be produced, but they'll be moving in opposite directions. 6a, 2 gamma photons will be produced and will have same frequency / energy. Okay, and will be moving in opposite directions. So that will get you 3 marks to give you those, mentioning those key properties. Let's look at part 2 now. So a proton and an antiproton are moving with almost the same high speed and in the same direction. Each possesses 8 × 10⁻11 joules of kinetic energy. The 2 particles meet. Calculate the frequency of the gamma photons produced. Okay, so I've already stated the equation, and basically we want the frequency of the gamma photons. I need to make a note of this, 8 × 10⁻11 joules as the kinetic energy. Here's the general equation here. And I want to work out my F. So again, we're going to use the mass of the protons. So I'm going to do 2 lots times mass, which is 1.67 × 10⁻27 kilograms, plus 2 lots of the kinetic energy, and that was given to us in the question. So 2 lots of 8 × 10⁻11 joules, and that's going to equal 2 lots of Planck's constant. And again, you can find this in your data sheet. It's 8.83 × 10⁻34 times F. Okay, so now we've got 2 unknowns. We've got 1 unknown, so we need to solve for F. So therefore, F is going to be okay, and you should end up with something close to 3.47 × 10⁻23 hertz. And we're on to the last one. So describe the process of fission and fusion of nuclei. Distinguish clearly between them by highlighting 1 similarity and 1 difference between the 2 processes, and state the conditions required for each process to occur in a sustained manner. So I'm going to say 1 similarity, which is the obvious one, between both fusion and fission reactions is that energy gets released. Okay, so we obviously, I mean, that's the point of fusion or fission, or at least one of the products of it. We obviously artificially use nuclear fission on Earth to get energy released, and we know that energy gets released from the sun or in the sun via fusion. Okay, so that's 1 similarity, and I think what else do they want us to say? 1 difference between the 2 processes, so we can just mention the difference in the processes. So 1 difference. So light nuclei fuse together in fusion. Okay, whereas in fission, heavy nuclei are okay, so I've said whereas in fission we have heavy nuclei absorbing a neutron, and then that leads to them splitting to daughter nuclei, and then energy gets released. Now, obviously, this is a 7-mark question. So I need to also state the conditions required for each process to occur in a sustained manner. So I'm going to say nuclear fusion requires high pressure and temperature. And I'm going to say fission requires uranium-235. So we want the correct isotope. And remember, I talked about at least you hear the word or the sentence uranium enrichment in Iran. And of course, it's not as simple as simply getting the uranium. You need to actually refine it to the correct isotope before you can get good nuclear fission occurring. So yes, we want the right isotope first of all, and then control rods and a moderator. Okay, so I've stated the conditions for both types of reactions. Obviously, one nuclear fusion, which at the moment we don't have large nuclear fusion power plants, but if we were to have them, they would have to be able to withstand very high pressure and high temperatures for that to occur long term. Fission, on the other hand, we know how to use. We need control rods and a moderator to reduce the speed of the neutrons, also absorb some of them to have a sustained and controllable nuclear fission reaction. Okay, so if you cover those points in your own words, that's perfectly acceptable. And also you could say these are at lower temperatures. So actually, the good thing about nuclear fission power plants also, they actually don't need to be at such high temperatures with respect to nuclear fusion power plants theoretically, okay? I mean, they do generate heat when the energy does get released. However, we don't need to supply energy in the first place. And we're on to the last one. So the fission of a uranium-235 nucleus releases about 200 MeV of energy, whereas the fusion of 4 hydrogen, 1 nuclei, releases about 28 MeV. However, the energy released in the fission of 1 kilogram of uranium-235 is less than the average released in the fusion of 1 kilogram of hydrogen-1. Explain this by considering the number of particles in 1 kilogram of each. Okay, so they make a good point. They say, well, if the uranium-235 nucleus releases this and it's undergoing nuclear fission, how on earth does and 4 hydrogen, 1 nuclei releases 28 MeV? How is that possible? Surely doesn't fusion release more energy than nuclear fission? Well, we've got to look carefully because how many nucleons are involved? First of all, okay, there's 4 hydrogen nucleons. And remember, a hydrogen, 1 nuclei is just literally a proton. So we've got 4 protons here, and they fuse together and they release 28 MeV. So 7b, so we know 28 MeV is released per 4 hydrogen, 1 isotopes. So therefore, 1 proton or 1 nucleon releases 28 divided by 4, which is 7 MeV. Okay, whereas the 235, so we have 200 MeV is released per 235 nucleons. So therefore, we'd have to do 200 over 235, and that gives us 0.85. And now this is a better comparison, okay? Per nucleon in the uranium, you get actually just 0.85 MeV, whereas you get 7 MeV for the proton in the fusion. So therefore, how many times greater? Well, if we do 7 with 0.85, okay, that's approximately 8.2 times greater energy released. Okay, so that's the sort of calculation you would want to do. So you've got to tell the examiner that, okay, well, what's really important is the energy per nucleon as opposed to just one large nuclei and 4 small nuclei. And therefore, we can say 1 kilogram of hydrogen, 1 isotopes, will therefore release more energy compared to 1 kilogram of uranium-235 nuclei. Okay, now this is a fair comparison. Now we've got 235 equivalent, 235 competitors on one football team of the hydrogen, and we've got 235 competitors on the uranium football team.